Thank you everyone for attending the September Soils Knowledge webinar today, our 46th by my count. So I'd like to introduce Guna Nachumutu, who's a research scientist in our soils unit here at DPI, and he's located in Narrabri. Guna's research focuses on long-term changes in soil health and productivity in cotton farming systems, and his recent project has involved accounting for carbon balances in these farming systems, and that's why he's going to talk about what he's going to talk about today. So let's get started.
Thanks, Abhi. Good morning, everyone, and I welcome you all to the webinar. Today, I will be covering the recent carbon balance research in the irrigated cotton farming systems with a special focus on the movement of carbon in runoff, drainage, and irrigation water. So in this webinar, I am going to cover on soil organic carbon and land use change briefly, and soil and stubble management in the cotton field, carbon sequestration in the cotton fields, and carbon balance in hydrological pathways. Within that, I will be covering surface runoff losses, closed irrigation network and how it impacts the nutrient cycling, and drainage carbon losses, and carbon inputs by irrigation water, and carbon balance. In this slide, I will explain the soil organic carbon balance in general. As some of you are aware, soil organic carbon balance is a function of organic inputs and outputs. Soil organic carbon balance will be altered significantly if there is a land use change. For example, if there is a land clearance to convert the pasture or forestry to cropping, there will be a negative balance, what we are seeing here, and then it will reach a new equilibrium. And similarly, if a cropping land is converted back to forestry, the soil organic carbon will build up and there will be a positive balance and it will reach another new equilibrium. Now, getting into cotton, for those who are outside the cotton growing regions, this slide explains the cotton growing regions in New South Wales and Queensland. As you can see, cotton is grown from central highlands in Emerald all the way to the southern New South Wales under a few different climatic conditions. Now, moving into cotton growing soils, this slide explains briefly on characteristics of sample cotton growing soil. The soil in the picture is cracking clay soil in Namoi Valley. It is a self-mulching wet-of-soil with 64% clay and alkaline pH. And sodicity at depth is usually greater than 6. However, based on my own observation over the past 4 years, the fields that are close to the river are non-sodic. And as you move away from the river, sodicity tends to increase. I have noted this within ACRI fields as well. In the next few slides, I will be showing some pictures of soil and stubble management in cotton fields, as it is directly related to biomass carbon return from residues and also its management. And this picture shows the strips of cotton field before and after picking. This picture shows the stubbles getting mulched. This is the next operation after harvesting. So the days of pulling, raking, and burning stubbles are the thing of the past, and it's no longer a common practice. Mulching along with defoliation can return up to 8 tons of dry biomass, which is approximately 3.2 tons of carbon per hectare. And here is an example of strips before and after mulching. Just I'm presenting this to give you an idea of the amount of stubbles that's going in. And the next step in the post-harvest operation is the root cutting, done about 2 to 5 centimeters below the surface. This is done to prevent the cotton plant from growing again, as cotton is an indeterminate perennial plant and it can harbor pest if it is grown off-season. So the next step, usually until the Bolgard 2 era in cotton, is the pupae busting to expose and kill any pupae of Helicoverpa that survived the Bt toxins. This is pest resistance management strategy for BT cotton. This operation disturbs the top 10 centimeter of the soil. However, the Bolgard 3, the new latest released Bolgard 3 varieties, gives relaxation from pupae busting for growers who were able to defoliate before 31st of March. So cotton growers have a choice of avoiding soil disturbance if they wish to minimize the tillage operations. And this is how the field looks before and after pupae busting. This picture shows the field before planting with fine till. So growers use additional tillage to apply fertilizers. Sometimes they combine the pupae busting with tillage operation as well. So usually the cotton stubbles are incorporated into the soil rather than being left on the surface. So it enhances the quick breakdown. And in this slide, I am showing photos of cotton fields across valleys and the level of organic matters. The first field is in Mori. It was taken in July 2017. The field came out of chickpea rotation and going into cotton. The other field I'm showing here in the top photo is in southern New South Wales, which was taken recently. This field came out of cotton and pretty much the stubbles were incorporated. And this field is going to be fallow for the next season. And what we are seeing in the bottom two photos are the one field with good stubbles and the other without stubbles, and they both are from the same farm in Narromine. And grower of this farm mentioned the stubbles give very good protection to cotton seedlings with healthy establishment. This is one of the best management practices to improve soil organic carbon and soil health. The grower is realizing the benefit with healthy crop establishment. Now, I'm going to explain briefly on carbon inputs and losses in the cotton field. In terms of cotton biomass return, it can range from 4 to 8 tons per hectare. I mean, in terms of dry biomass, which is approximately 1.6 to 3.2 tons of carbon. Roughly 40% of the biomass is carbon. Similarly, the corn, which is a cereal crop and a summer cereal crop, now some of the growers are incorporating that into their rotations, also returns around 8 tons of biomass, dry biomass, with the carbon inputs of about 3.2 tons per hectare. Also, cotton growers apply a range of fertilizers. The amount of carbon fertilizers added, amount of carbon added with the fertilizers depend on the type of fertilizer applied. For example, 650 kg per hectare of urea can contribute 130 units of carbon per hectare. And also, some of the cotton growers in the southern New South Wales apply chicken manures, and the amount of carbon added depends on the volume of organic inputs added, and also the amount of carbon within those inputs. And the other source of carbon inputs to the irrigated systems is the irrigation water and dust storms. As you can see in the photo, the water also brings in a lot of sediments. It's a bit murky. The carbon contribution by irrigation water was not quantified in the past. I will be presenting result of the experiment we conducted over 3 years related to this bit later. In terms of losses, bulk of the added biomass is believed to be lost by microbial decomposition. However, the unknown factor so far in the irrigated system is the carbon losses associated with the irrigation runoff, erosion, and drainage. I will be covering on this in later slides. So this slide explains the trend of soil organic carbon in the long-term trial running since 1985 in Australian Cotton Research Institute. X-axis is the time series and y-axis is the soil organic carbon stocks to 60 centimeter depth. The three treatments shown here are conventional tillage cotton monoculture, minimum tillage cotton monoculture, and minimum tillage cotton wheat rotation. So what we see here is the decline in soil organic carbon after a land use change. So the field was brought into cotton in the 1970s. The soil organic carbon decline continues and is moving towards an equilibrium. as I have explained in the earlier slide on the relationship between land use change and soil organic carbon. Also, the cotton wheat rotation only reduced the rate of soil organic carbon decline. Still, the decline continues. However, in the present circumstances of commercial farming, reducing the rate of decline itself is a positive aspect here for that particular management practice. As we have seen one particular field in the previous slide, this slide explains the soil organic carbon sequestration rates reported in Australian cotton farms. I like to acknowledge Nilantha and Ian Rochester for their long-term work on soil carbon. Most of the farms are showing a negative balance, as you can see here, except 2 trials in ACRI. These 2 are the same trials, and this is another trial showing a positive balance. So here, some specific rotation management practices are showing positive balance. The treatment showing positive balance of soil organic carbon is the cropping system that included wedge rotation. And here again, this field also included wedge rotation. And wedge not only contributes carbon, it also contributes nitrogen. And in one of these trials, which was left as a surface mulch in this treatment, and here in this trial, which was incorporated into the soil. So irrespective of whether it's surface mulch or incorporation, both have shown positive benefits to soil organic carbon. So now I'm going to take you through the 3-year field experiment we conducted to quantify the carbon flow in terrestrial hydrological pathways. The experiment was conducted from 2014 to 2017. Going into the background of the research, the theoretical estimates of soil organic carbon sequestration often does not coincide with the measured values. As I explained to you before regarding the carbon inputs and losses, there is a general assumption that most of the carbon losses in cropping soils are due to respiration losses. In 2013, there was a special issue on soil carbon in Australian farming systems in the journal Soil Research. Most of the papers focused on respiration losses, and there is little information on carbon gains through irrigation or losses through runoff and erosion. So the research question we asked here is the annual carbon flow through terrestrial hydrological pathways contribute to the carbon decline or sequestration in cotton farming systems? So this slide explains the treatments within the long-term trial where we conducted this experiment. The experiment includes 3 historical cropping systems: maximum tillage cotton monoculture, minimum tillage cotton monoculture, and minimum tillage cotton wheat rotation. These treatments were implemented in 1985. In 2011, Nilantha subdivided these treatments and introduced maize rotation into each of those 3 cropping systems by redesigning the trial into split plot. So the 3 treatments got converted into 6 treatments with 3 systems incorporating the maize rotation and 3 systems continuing as historical cropping systems. So the trial includes 4 replications. The picture above shows the location of the flumes and runoff monitoring equipments. So we had 2 flumes in the head ditch and 6 flumes in the tail drain to measure the runoff. And the field also had a lysimeter until this year managed by CSIRO, and it's no longer existing. To explain a bit more on the runoff monitoring and sampling, we used ISCO auto samplers with a logger to measure the flow height. I programmed the sampler to flow weighted sampling as it is the best sampling strategy to get a good average concentration for the entire flow. And we also measured the deep drainage using chloride mass balance modeling by measuring the chloride content in the soil sampled before planting and after harvest. Now, in this slide, I'm going to explain the recent trend in soil organic carbon. So please don't get confused. So this is, I'm going back into the soil organic carbon levels, not the soil carbon in irrigation, water, or drainage. So x-axis is the timeline and y-axis shows the soil organic carbon percentage. And the first three compartments are historical cropping systems. And the second three compartments are those with maize rotations. And M and T is the minimum tillage, and M and W is the minimum tillage wheat rotation, and MXT is the maximum tillage. And the different colors indicates the different depth increments. So we sample the soil 0 to 15, 15 to 30, 30 to 45, 45 to 60, 60 to 120 centimeter depth increments. And what we have seen here is the corn rotations improve the soil organic carbon in short term in the topsoil. However, you can see there is a decline in the subsoil. The improvement in soil organic carbon is more pronounced under maximum tillage. As you can see here, there is a bulk increase in the topsoil. So in summary, what this is the short-term increase and decline suggests the soil organic carbon is reaching an equilibrium level for cropping. So now I am getting into the hydrological pathways. So in this slide, I am presenting the runoff results. The table shows the average runoff per irrigation. In the 3 years of monitoring, the runoff in the minimum tillage was always higher than the maximum tillage. However, the water use efficiency is always higher under minimum tillage, as the yield was better under minimum tillage. To explain in simple terms, both plots were applied with the same volume of water. However, more water was recirculated to the dam under minimum tillage. I will explain about the recirculation in next couple of slides. Thus, so since more water was recirculated back, thus resulting in better water use efficiency under minimum tillage. I also want to alert you to the fact the length of the furrows are only 190 meters long, typically designed to finish the irrigation within public service hours. The commercial farms would have up to 1,000-meter long furrows, and the irrigation run time is a lot higher. And we analyzed carbon fractions in runoff samples using American Public Health Association method, which is a standard method for analyzing the nutrients in the runoff water. Okay, while talking about runoff, I should clarify that the water leaving the cotton farms are not moving off farm. So the cotton farm layout is designed in a way that most of the runoff water is recirculated back into the on-farm storage, and this also happens during rainfall. So except during major flooding, water is pretty much recirculated and stored on farm. So the design of the cotton farm is sustainable in terms of water use, and this also minimizes the off-farm impact by minimizing the off-farm nutrient movement and transport. So this is the river, and then once the water gets pumped into the on-farm dam, so it gets irrigated into the field, and from the main tail drain, this goes to a point close to the dam where all the water is pumped back into the on-farm storage. In this slide, I'm giving a bit more explanation on the closed irrigation network with an example of the ACRI research farm. The farm is located adjacent to the Namoy River, and as you can see, I explained it in the previous slide. So the water will get pumped and circulated back through this is the main tail drain, and this usually gets pumped back into this dam. So there is no escape of runoff water from the farm. And this recirculation has implications for nutrient cycling in hydrological pathways. So this graph explains the seasonal carbon losses in runoff. The carbon losses ranged from 24 to 61 kg per hectare. The total organic carbon losses ranged from 24 to 61 kg per hectare. And the dissolved organic carbon fraction is approximately 85 to 97% of total organic carbon. So in this graph, I'm explaining the DOC flux in runoff water in 2014-15 season. The x-axis is the days from the first irrigation, and y-axis is the dissolved organic carbon loads moving out in runoff water. And as you can see, there is a general decline in carbon load as the season progressed, which is expected. Considering maize and cotton rotations, there was an initial spike in the dissolved organic carbon loads under minimum tillage maize rotation systems, which disappeared later. And this trend was slightly different in 2016-17 season, where the DOC load increased in the mid-season. You can see in all the treatments that happen. This spike could be related to the water source or the irrigation water inputs, which I will show after the next couple of slides. And we also measured the leaching of carbon in the soil profile. We installed about 48 ceramic cup samplers, 24 samplers at 60 centimeter depth, and 24 samplers at 1.2 meter depth. And we created suction just before the irrigation, and we collected leachate samples 3 days after irrigation. We measured the dissolved organic carbon, and what we found in the first year was the samples collected from the maize fields had significantly higher dissolved organic carbon levels compared to those with the history of continuous cotton. So you can see the difference here. This higher DOC concentration could be related to the leachate from the topsoil, from the decomposing maize residues, or the decomposition of the maize roots at depths. And this also explains the soil organic carbon decline at depths in the maize systems that I presented a while ago. Okay, this graph explains the results of dissolved organic carbon gains in irrigation water. The carbon gains from the irrigation water ranged from 4 to 102 kg per hectare per irrigation, and the seasonal dissolved organic carbon gains ranged from 66 to 226 kg per hectare. Also, you can see there is a spike in dissolved organic carbon loads in the mid-season in 2016-17 season, and this was reflected in the runoff loads that I explained you a couple of slides earlier. Now, in this slide, I am presenting the net carbon balance results for terrestrial hydrological pathways. The total carbon gains in the irrigation water ranged from 72 to 248 kg per hectare, and the carbon losses in runoff ranged from 30 to 43 kg per hectare, and the carbon losses in drainage ranged from 2 to 22 kg per hectare across 3 years. And this resulted in the positive balance of net positive balance of 19 to 201 kg per hectare across 3 years. And when we compare this quantity with soil organic carbon stocks, the net carbon gains during irrigation is relatively a very minor proportion. However, under irrigated farming system, this quantity is considerable proportion in terms of carbon improvement in the soil. I will explain a bit more detail in the next slide. So in this slide, I am going to explain how the net total organic carbon gains during irrigation are related to annual soil organic carbon sequestration rates or decline in cotton farming systems. I am grabbing a couple of examples I presented earlier about the carbon sequestration rates. For example, the first field where the annual carbon balance is in decline at the rate of 870 kg per hectare per year. In this context, the carbon gains from the irrigation water can mitigate up to 23% of the decline based on the results over last 3 years, what we observed. And similarly, according to Ian Rochester, the annual carbon sequestration rate is around 280 kg carbon per hectare per year. And given that field is also located in Australian Cotton Research Institute, and if we assume that the field also receives similar carbon content in irrigation water, carbon gained by the irrigation water can account up to 72% of the annual sequestration rate. So what I did was I divided this 201 by 280 and multiplied by 100 to get the 72%. So in terms of annual carbon sequestration rates, the carbon gains from the irrigation water contributes to a considerable proportion. I hope this is clear to everyone. So to summarize, the carbon balance through hydrological pathways is a considerable proportion of annual soil organic carbon sequestration or decline rates. And the future carbon balance studies in the irrigated farming systems need to account carbon balance in hydrological pathways. And the soil management should consider improving or at least sustaining the soil carbon. And in the process of soil management, any improvement in soil organic carbon stocks is a bonus for growers. And also what you are seeing in this picture is the burnt tree roots that hit our soil core a couple of years ago. And this is a clear evidence of land use change, and still, because the field is brought into cotton only in 1970s, and still what we are seeing is the reflection of land use change. And there are a few other related CRDC projects that are currently under progress, which include the soil system projects run by Oliver Knox and team at UNE. And within that project, Yui Osanai is working on carbon and nitrogen cycling of whole profile in cotton farming systems, and Catherine Pauline is working on whole profile microbial dynamics. And I would suggest everyone to look for some publications in the near future to learn a bit more on the science of whole profile soil organic carbon mechanisms. And I like to thank CRDC and NSW-DPI for funding this research, and Cottonseed Distributors and DuPont Pioneer for supplying seeds for the trial. I also like to thank all technical staff and ACRI farm staff assisted with this project. Thanks again to all of you for your participation in the webinar. Any questions?
Thank you, Guna. That was great. And yeah, thank you everyone for participating today in this month's webinar.
Thanks, Adi.